All right, we are back. Thank you everyone for coming out to join us for Astronomy on Tap virtual number 5. This has been a pretty good learning experience for us, getting things online. I think we're kind of getting into the groove. Still going to be a few missteps, I'm sure, but we'll make it through. So tonight we have a very spooky show for you in store. It is Halloween, of course, so we'll be talking about spooky exploding stars, apologize, and spooky storms on other exoplanets. My name is Michael Roderick, and together with Jacob Lund and Arvind Gupta, we run Astronomy on Tap State College. So if this is your first time checking us out, welcome. The way this is going to work is after this introduction, Jacob is going to show you how to make our astronomy themed cocktail. Then we'll have our first talk of the night by Thomas Beatty, followed by trivia with Arvind, astronomy in the news with Jacob, our last talk of the evening with Dr. Raffaella's group at Northwestern, and then our trivia answers, and then we finally say our goodbyes. So with that being said, I'm going to go ahead and get started and pass this over to Jacob Lund, who's going to show us how to make our astronomy themed cocktail. Go ahead, Jacob.
Great. Thank you, Michael. So tonight we're going to be making a spritzer. And the reason for this, maybe if you were paying attention on those introductory slides, one of our talks tonight is going to be talking about storms on other worlds and specifically using the Spitzer Space Telescope. And so tonight we're going to be making a Spitzer spritzer. So to do that, hopefully you saw the ingredients there. We're going to be using a citrus aperitif. But if you don't have that, you can also use bitters and vermouth. It's a slightly different flavor, but comes out kind of the same. But then also we'll have some Blue Moon, some simple syrup, and some sparkling water. So to start off, you start with the aperitif. And you want about 1 shot's worth of that. And it's very red. I'll try not to spill. Ooh, I think I did it. Nice. And then you'll take 2 ounces of the sparkling water. And I like to make it a little sparklier, so I'll put in an extra splash. And then now we're going to add simple syrup. Simple syrup. Oh, hands are wet. And for this, do a little less than half an ounce, although I'm going to probably do close to 2 now, half an ounce, just because it's sort of measuring it by eye. Gives it a bit of a sweeter flavor, helps balance out a little bit of the bitter aperitif. And then we're going to need half an ounce of lemon, but we're also going to need a lemon spiral, which I'm going to do my best. I've only done this once before. But we'll use this to garnish at the end. So I'm going to cut this off. That's spirally enough. That'll work. And now just about the juice of half of 1 lemon. And we'll just go ahead and just put that all in there. And we'll give it a good stir. And lastly comes the Blue Moon. As usual, we're making beer tails because this is Astronomy on Tap, and so we like to keep that beer theme going on. So just a little bit of Blue Moon, 3 ounces. I don't remember if I said that already. Just add that to the top. And then we'll top with some ice cubes, some fresh, cold ice cubes. And then put our little lemon spiral garnish up at the top, and that is our Spitzer spritzer. And it's red because the Spitzer Space Telescope looks in the infrared, and that's how it's able to see things like atmospheres. And so it also has you can maybe think a little bit spooky, maybe think of it as some drops of blood in your potion or something, if you want to take it that way as well. So here's our Spitzer Spritzer. Cheers.
Cheers. So say if you really want to be authentic, get that knife as you're cutting that lemon spiral and get some blood in there.
Yeah.
Not too bad. All right, thank you, Jacob. So with our drinks in hand, I think we are ready to go ahead and get started for the night. So our first talk is going to be by a man who was actually at Penn State not too long ago for a postdoc, Dr. Thomas Beatty, who is now at University of Arizona, and is going to be telling us about spooky storms on exoplanets. So Thomas, whenever you're ready, go ahead and take it away.
All right, thanks, Michael. I'll admit I am not drinking a Spitzer Spritzer because I do not have the ingredients. I instead have, oh, can't really see it. I don't know, a little bit of whiskey to go with this.
We'll accept whiskey as well.
I know, it's not really in the spirit of astronomy on tap. Okay, is that showing up?
Yes.
All right, perfect. Yeah, so thanks. So this talk is going to be about spooky storms on other worlds. And this is running a little bit with the Halloween theme right now. But of course, in reality, storms usually aren't that spooky. They're a major part of our life on Earth. And this actually is a photograph of Earth that was taken about 6 hours ago by a spacecraft that's out in geostationary orbit called Discover. And I want to particularly thank this morning this particular storm. So I'm at the University of Arizona in Tucson, and those clouds were over us most of today and provided us with the first rain we've had for I think the last like 3 months. So in a lot of cases, storms can actually be pretty nice. But for thinking about other planets, right? When we think about Earth, like what causes storms, right? Storms on Earth are a reflection of the fact that we have this dynamic atmosphere on Earth that has lots of different constituents and it's in motion, right? It tells us about the fact that the Earth is rotating, that the atmosphere is constantly mixing, and it's that dynamic atmosphere which helps support life on Earth and also influences, the water cycle and a lot of the chemical balances about what's happening on the surface. So when we think about other planets, and if you're thinking about, say, finding life on them, or if you're thinking about just trying to measure, what are they made out of? Like, let's look at a planet and figure out what its atmosphere is made out of, what is the surface made out of. You have to think about what the weather on that planet is like. And even something as simple as this, right? Like this picture, this straight picture of Earth tells us something about the weather patterns. You can sort of see, if you know where to look, you can see the direction of the prevailing winds on Earth. Right, we have these westerly winds at the north and south poles, and then near the equator, we have what are called the trade winds that blow in the opposite direction. So Earth has, roughly speaking, we have these 4 different bands of winds that occur on the surface of the Earth. And that actually is telling us something about the rotation rate of the Earth. I'll talk later a little bit more about this, but the rotation rate of a planet really sets the number of bands you get here and what effect they have. For all you sailors out there, the ones down in the southern hemisphere, the blue arrows that blow westerly, are called the roaring 40s, because down in the southern hemisphere, it's mostly ocean, and so these winds just go across the ocean and kick up these gigantic waves. I had a friend of mine crewed on a sailboat that was sailing from Buenos Aires to Cape Town down in the roaring 40s, and I think he didn't really know what he was getting into. But he came up in Cape Town 2 weeks later and just looked like it was the most exhausting 2 weeks of his life, because they were just in constant high wind storms pretty much the whole ride across. So if anybody goes down there, just keep that in mind the next time you're down in the southern hemisphere on a sailboat. Okay, so that's Earth. I'll talk a little bit about the solar system to begin. So I've labeled here all of the solar system planets that have major atmospheres. So Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Mercury does not make the list. It doesn't really have an atmosphere. And you can see that Pluto and I think Quirrell is out there, but either of them really have atmospheres. All of the planets in the solar system that have atmospheres have some sort of storms and some sort of weather. So if we want to try and understand, as I was saying, we want to try and understand Earth, we want to try and understand exoplanets. If we want to try and understand solar system planets, we also need to understand what their weather is like. So the first one, and probably the closest to our experience on Earth, is Venus. So this is a picture of Venus. It is completely covered in clouds. You'll see sometimes if you look, on the internet, or people have, pictures of Venus that they use in news articles or something. They'll show you this sort of orangish blob and say this is what Venus looks like. This is actually a colored in. It's a radar map of Venus's surface. You can't actually take pictures of Venus's surface because it's covered in clouds. So this is a radar map from the Magellan spacecraft from about 20 years ago. This is not actually what Venus looks like, right? If you actually were looking at Venus, you would see these clouds. And if you were on the surface of Venus, this is one of the few pictures we have from the surface of Venus. The color is sort of a yellowish, and it's very cloudy. The visibility is probably only like a mile or probably less than that because it's just constant clouds everywhere. One thing to note just about the storms, right, is I was talking about how rotation sets a lot of what's going on Earth. And the same thing is true for Venus. And Venus is very particular because in many ways it's very similar to Earth. It has a mass that's almost the same as Earth. It's almost the same radius. It's very close in size to Earth. It's closer to the sun, but it's not too much closer. The average temperature on Earth is probably about 50 or 60 degrees Fahrenheit. The average temperature on Venus would be 90 degrees Fahrenheit. That's not great, but it's not killer. The real difference between Earth and Venus, for one of them, is that Venus rotates incredibly slowly. So on Earth, the Earth takes 24 hours to do one rotation of the Earth. Venus takes 273 days to do one rotation. It's almost stationary in space with regards to its rotation. So what that means is that on Earth, we have these four bands of weather that are crisscrossing the planet. On Venus, there's one central sort of band along the equator. You can sort of see this if you look at the cloud features. There's one sort of general direction that everything travels. And that's telling us, just by looking at that, we could say something about what Venus's underlying rotation rate is like. So that's telling us that the rotation rate is super slow. So even though there are clouds here and we can't see the surface, we can sort of get an idea of what the surface is like. Of course, Venus, another reason why Venus is different from Earth is that it's, I don't want to say it's a hellhole, but it's not a great place to visit. Venus's clouds are almost entirely made out of sulfuric acid, which is probably better known as the battery acid that you get in like a car battery. If the acid from a car battery starts spilling everywhere, that's what Venus's clouds are made out of. So I showed you before this picture of a spacecraft that landed on the surface of Venus. This is called Venera 13. It was a Soviet lander from the 1980s. Venera 13 only lasted on the surface for about 45 minutes, maybe 60 minutes, before it was dissolved by the sulfuric acid in Venus's atmosphere. So Venus is not a nice place to visit, and it's very difficult to get down to the surface. So this is why this is one of the only pictures we have. Actually, a fun story about this lander was that it also had a soil probe, a little scoop arm that was on a spring, and once it landed, the spring released, and the scoop arm was going to shoot out, grab some dirt, and then pull it back in and dump it into a little laboratory that was on the lander. The only problem is that the lens cap, right? The camera that took this picture had a lens cap on it that was on during the entry because it's heating up, right, as it's coming into the atmosphere. So they need a lens cap to protect it. Once it's on its parachute and it's drifting down, the lens cap popped off and they started taking pictures. Anyways, they land, they release the spring, the arm shoots out and goes directly into the lens cap that had landed about 2 feet away from the spacecraft. So they did not actually end up getting anything in the sample arm, which I can only assume the people who were in charge of that experiment just probably started drinking heavily. Maybe because they were Russian too. One interesting thing, though, about the fact that Venus's clouds are made of sulfuric acid is that if you could actually stand on Venus, and I put smells there in quotation marks because the idea of smelling the atmosphere of Venus doesn't really make any sense given what it's made out of. But if you could smell it, Venus would actually sort of smell like burnt matches. The burnt match smell you get is from the sulfur that's in the match head that's been burnt and oxidized into sulfur dioxide, and that's a major component of sulfuric acid. So the atmosphere, the predominant smell in Venus would be like burnt matches if we could somehow smell this atmosphere safely. The atmosphere itself is almost entirely carbon dioxide. The little bit of sulfur dioxide you can see there, that's what makes up a lot of the clouds, but it's a lot of carbon dioxide. Compare that to Earth, where most of our atmosphere is nitrogen and oxygen, and carbon dioxide is less than 1%. It's about 0.5%. Right? Carbon dioxide on Venus's atmosphere it's almost 100% of the atmosphere. And that's why Venus is so much hotter than the Earth. The temperature on Venus is several hundred degrees. And that's directly because the carbon dioxide in the atmosphere creates this super greenhouse effect that just completely boils off anything on the surface. So the surface, as you saw in those pictures, is just this sort of rock, and it's not really dirt, it's sort of just loose rock mixture that's covered in this sulfuric acid. It's getting superheated by this carbon dioxide atmosphere. And actually, even that is sort of understating it, because Venus's atmospheric pressure at its surface is about 100 times the pressure on Earth. So there's a lot of reasons why Venus is a very difficult place to visit. Okay, what about the other planets in our solar system? So the largest planet that we have is Jupiter. Jupiter also has a lot of clouds and a lot of storm systems, and in many ways is a lot more dynamic than Venus. Remember that Venus is rotating so slowly that it really only has this single sort of jet. If you remember the photograph, it looked almost featureless, right? Venus looks almost featureless. The clouds are sort of well mixed. It has this one sort of broad band that you can sort of make out from the center. Meanwhile, Jupiter has these multiple bands. You can see there's these gigantic storm clouds, these circular features like the Great Red Spot. You can see the mixing, the sort of shear layers in between the different bands. So Jupiter's atmosphere is a lot more dynamic than Venus's. And that's telling us something about what is going on inside the planet, right? So because it's so much more dynamic, you also have a lot more just sort of vocabulary here. I'm not really going to use this. I'm sort of showing this just because, you know, the people who work on Jupiter spend a lot of time about sort of categorizing and thinking about, you know, okay, like, is this the North Tropical Zone or the North Equatorial Belt or the Equatorial Zone? In large part because those are very different dynamical parts of the atmosphere, right? If you make if you sort of draw out what is the wind speed on Jupiter, it almost perfectly corresponds to these bands, right? So Jupiter's bands occur because Jupiter is rotating incredibly fast. So Jupiter takes about 10 hours to do one complete rotation. Remember, the Earth takes 24, Venus took 273 days. Jupiter does it in 10 hours. And Jupiter is 10 times larger than the Earth. So it's rotating about 20 times faster than the Earth. And so what that means is you get all these bands and you get these very strong winds. And the winds alternate sort of forward and backwards as you work your way across the planet. And that's what causes these bands to form and what causes these shear layers in between them. And it causes also a lot of mixing in Jupiter's atmosphere. So the components of Jupiter's atmosphere, they're always being stirred, and there's a lot of mixing around happening, and things are being dredged up. And so measuring like what is the composition of Jupiter is actually a pretty interesting problem, because everything's always being sort of stirred around. And you'd think that that would give you a pretty well mixed, you know, set of atmosphere that you could go try and measure. In reality, what that means is you actually get these sorts of pockets that sort of form and dissipate and form and go away. Back in the 90s, there was a spacecraft called Galileo that went to Jupiter and dropped a probe into Jupiter's atmosphere. So it fell into the planet, parachutes came out, and it drifted down a couple hundred miles into the atmosphere. What it found was that there was almost no water. It measured almost no water in Jupiter's atmosphere. And everybody was super confused by this until we went back and we realized that actually the entry probe had just landed in almost like the driest part of Jupiter's atmosphere, right? It had hit one of these pockets that was caused by all this mixing and turbulence and stuff. And so what we got was this very particular and frankly sort of wrong image of what Jupiter's atmosphere looked like from the entry probe data, that we now know that Jupiter's atmosphere is much different than what we would have thought, back in the 90s when people first started getting these results. Of course, the major feature on Jupiter, if you look at it, is the Great Red Spot. The Great Red Spot has been around for at least 400 years. The first reported instance of somebody observing it is in 1664 with one of the very earliest telescopes. So the Great Red Spot has been around a long time. The Great Red Spot is also gigantic. So I think we often forget how large Jupiter is. The Great Red Spot is about twice the size of the Earth. So it's this gigantic storm system that has been around for about 400 years and has maintained itself in Jupiter's atmosphere for all that time. It's not actually really clear why the Great Red Spot exists, or at least why has it maintained itself for 400 years. It probably has something to do with the fact that it sort of sits right in between these two cloud bands you can see, the South Equatorial Belt and the South Tropical Zone, if you're reading the labels. But that presumably has something to do with it because it's sort of causing this cyclonic circular motion. But what actually causes the Great Red Spot is not very well understood. And it's actually even more confusing because the Great Red Spot is actually shrinking. So this is on the left is a photograph from 1973 from the Pioneer 10 spacecraft that flew by Jupiter. And on the right is a Hubble Space Telescope image from just last year. And you can see that the Great Red Spot has gotten noticeably smaller over the last 50 years. It's almost halved in size in the last 50 years. Nobody understands why this is happening. It just suddenly started getting smaller. It's unclear if it's going to keep getting smaller, what's going to happen. We do know though that if it keeps going, if it keeps shrinking at its current rate, that the Great Red Spot will actually disappear sometime around the 2080s, which is telling us also something about the dynamics of these atmospheres. We think when we look at something like Jupiter and we see the Great Red Spot and all these bands that, it's been around for 400 years and it's gonna, the Great Red Spot is a permanent feature of Jupiter that, is definitely gonna be there all the time, right? But it's conceivable that in, 60 years, the Great Red Spot will have completely disappeared. People growing up, starting in the 2090s will never have seen the Great Red Spot and it won't be part of their conception of what Jupiter is like, right? These atmospheres are not these static objects that, have these features and maintain themselves. They're these very dynamic processes that come and go, much like what we see every day on Earth when you walk outside. Okay, so that's solar system planets. But what about outside the solar system? So we know about now over 1,000 planets around other stars that are, within a couple tens of light years out to, 1,000 light years or even more from the sun. So we have all these other planets outside the solar system that we can try and measure their atmospheres. One of the ways we can do this is we can use something called a phase curve. So remember that these planets are hundreds of light years away. A lot of them are very close to their stars. So we can't actually see them directly. We can't look at the star, look at the planet and take a picture. We wouldn't be able to separate them out into, the star and the planet. We wouldn't get a picture of that. We just see the star because the star is so much brighter. So instead we can look at both the star and the planet. And if you look continuously as the planet goes around the star, you get this thing called a phase curve, whereas the bright day side of the planet rotates into view. The whole star-planet system gets brighter. The planet goes behind the star. It drops down. That's the eclipse. You can see it occurs twice at the start and the end of these data. And then the night side rotates in, and then you have a transit. And what this does is by watching how that brightness comes up and then goes down, we can map the exoplanet in longitude. So we can create these longitudinal maps of what the exoplanet looks like. And actually, these particular data are from Spitzer. So Jacob mentioned Spitzer for the theme of the cocktail. Spitzer has done almost all of these observations that we have for exoplanets. And the reason for that is that Spitzer is an infrared telescope. Most of what we've seen are hot Jupiters, which are heated up to temperatures of about 6,000 degrees Fahrenheit. So these are incredibly hot atmospheres that radiate a lot of energy in the infrared. So Spitzer as an infrared telescope is perfectly placed to try and measure what's going on here. So we do actually see signatures of clouds on hot Jupiters. These are actually plots in a paper that I just submitted that are from a phase curve observation of a planet. And what we saw is we were able to map using that phase curve. Remember, you get the longitudinal map. We were able to map the cloud cover as a function of longitude. And what we can see is that, these exoplanets mostly have completely cloudy nights. As soon as the star goes down, the clouds start forming, and they get almost complete cloud coverage on their night sides. And then once you get back to the day side, remember they're getting heated up to like 6,000 degrees. So they get to the day side, they start getting hammered by this starlight that's heating everything up. The clouds all start burning off. And they start evaporating and burning off over the course of the morning until you get to the afternoon, and you get sort of a almost entirely clear afternoon, and then you go back. So again, these very dynamic atmospheres with variable cloud cover and presumably a lot of weather happening as a result of this. One interesting thing is that there's actually, if you look at the observations we got compared to simulations, the simulations say that there should be almost no cloud cover on the day sides. There's a lot of reasons for that, but one that I like in particular is if you think about like how the simulations are run, it's really a scale issue. So when they run these simulations, they divide the entire planet up into this grid of like 128 by 96 little grid squares. And they use that and they simulate, what's going on in each grid square. And that sounds like a pretty fine resolution. You can see this little box right here. That's about the size of a grid square, right? So that's actually pretty good resolution on this map. But remember, this planet is about the size of Jupiter. That means that the actual physical size of a grid square is literally about the size of Mars. So we're simulating things that are about the size of Mars. That's the resolution of the simulation we have. But then what is the length scale? Like, what is the size that we care about for cloud formation? It's probably, it's literally probably like a couple of feet, or like the size of the room you're sitting in. So our grid squares are like the size of Mars, but to do clouds correctly, we need to simulate down at like the couple of feet level. So it's an incredibly difficult simulation challenge that nobody has quite figured out how to solve. It's also hard to do experiments with what we think these clouds are made out of, right? Remember I said these things are heated up to like 6,000 degrees. That means you get iron clouds, you get clouds, frankly, made out of sand, magnesium sulfide, all these weird things. And it's hard to do experiments because what you need to do is you need to get a bunch of hydrogen gas. Most of these atmospheres are hydrogen. You pressurize it, you heat it up to 6,000 degrees, you put some iron in it. So it made these, sort of iron dust grains, and then you'd shoot a laser at it to see, sort of what you get out the other side. And for, I guess, unsurprising safety reasons, a lot of universities are hesitant to let a bunch of scientists shoot high energy lasers into highly pressurized, high temperature hydrogen gas for fear of, what mistakes could be made. So the lab work here is actually very difficult to understand the cloud components. Okay, so that pretty much wraps it up. The title of this was Spooky Storms on Other Worlds, but in reality, storms, except if you get a really bad thunderstorm maybe, are not actually that spooky. And actually, by looking at the storms, they tell you a lot about what's going on in the planetary atmosphere, sort of the rotation, the surface, the composition, and they're really an important part of understanding, planets in our solar system and exoplanets when we look at planets around other stars. So I will leave it there with the end. Probably not, because we're going to keep looking at these clouds and learning more about it. And happy to take any questions.
Awesome. Thank you, Thomas. So again, if you have any questions, please type them into the chat. We can go ahead and ask Thomas while he's still here. So I got to ask, you have Venus and you have Tucson in June. Which one of those two is more conducive to life?
So that's a good question, Michael. I got to be honest. I feel like Venus right now seems at least like it would be a nice break of change of pace.
Fair enough. At least we're getting rain now. That's gotta be nice.
Yeah, we've been at above 100 degrees since like late May, and we just got below 100 like a week and a half ago. So I think everybody's morale is a little low. It's been a rough summer for a lot of reasons, but that in particular has been a real tough one.
Fair enough. So we got a few questions here from YouTube. So of course you mentioned Venus. Lots of news about Venus lately. What is kind of the status of that? I've seen some papers, some statements come out saying maybe this was bad data reduction, maybe this was not truly a significant discovery. What's going on with this potential discovery of life on Venus? Are there
So that's
aliens, Thomas? Are there aliens on Venus? Yes or no? Right now?
100%. It's covered. No, that actually, I was going to say that's what's called, you call the business leaving a leading question for the audience. Yeah. So life on Venus, I'd say it's still very much up in the air what's going on. There's been a lot of, as you said, Mike, a lot of papers flying back and forth about what's happening. So I'll say my personal opinion is that, okay, so what did they see? Is they saw what they thought was phosphine. They didn't actually see phosphine. This is interesting. They saw something else, and they saw like too much of it. So they said, well, the additional stuff has to be phosphine. And then they said, okay, we see phosphine, and we can't come up with any way to produce that other than with life. So there are two sort of worrisome parts about that argument. One, like you said, is they didn't actually see it directly. They just saw some additional like signal that they thought was phosphine. If that additional signal isn't there because it's a very difficult measurement to make, then there's no phosphine. And then even if there is phosphine, it's not clear. I would say it's not yet really clear if the statement, they said that there's no way for life to make there's no way to make this without life. I don't think that's quite true. This sounds a little catty. It might be better to say there's no way that they figured out for it to be made without
They
life.
did leave it very open, right? That we just don't understand Venus's chemistry very well, that it could very well be other things, right?
Right. The universe is a lot cleverer than we are in a lot of ways. So just because we can't figure out how it happens doesn't mean it can't. And I've talked to a couple of organic chemists who say, no, of course you can form phosphine. Here are the pathways. So I think even if there is phosphine, which I'm not sure there is, there's probably a pretty reasonable. I think there's probably a reasonable chemical pathway that doesn't involve life. So I would be pretty skeptical of life on Venus until the dust settles in a couple of months.
Okay. Also, we've got a bit of a debate going on in the chat right now. How exactly do we know the rotation of Venus? And kind of following up on that, how do we know the rotation of gas giants like Jupiter, especially if they have bands that are rotating at different speeds?
That's a super. I actually always get that question about rotation rates of gas giants, even when I give talks to PhD astronomers. So that's a super good question. The rotation rate of Venus. So the rotation rate of Venus wasn't known until the 60s, when in the 60s they started doing radar observations. So they'd point a high-powered radar at Venus, they bounce radar, off it, look at the returns, and that allowed you to measure what was happening on the surface. And then in the 90s, we had Magellan, which orbited Venus and used a radar mapper on it. So really, the way we know the rotation rate of Venus is with radar, we can see through the clouds and we can see the surface. And that allows us to measure what the rotation rate is. For the gas giants, right, so there's two things to think about, right? Like on Earth, we have the surface of the Earth, or on Venus for that matter, is rotating, right? And that's a pretty easy thing to understand. The surface is rotating. And then on top of that, we have the atmosphere. And the atmosphere can be rotating differently. It actually is, right? That's why we have winds and jet streams. That's the atmosphere on Earth rotating faster than the actual surface of the Earth spins. So the atmosphere can be decoupled from the surface. On a gas giant, that happens a little bit, right? Like what happens is that there's the top layer that we can see that's rotating, at some speed. But then as you go down, you don't get a surface, but you get these incredibly dense core, and that's rotating at some speed as well. And using spacecraft measurements, you can measure what that core is doing. So you can think about like what the bulk, sort of what the planet's doing on average, and then what the atmosphere is doing. So, and the way the spacecraft work is you map out the gravity field, and you can actually see it rotating a little bit. You can see signatures of rotation in the gravity field because Jupiter's gravity is not uniform. So that's actually how they measure it.
Okay, so kind of a related question here is, do we know what is like the ground or the core's rotation speed of Jupiter? How does that compare to the rotation of its atmosphere?
Yeah, so the rotation rate of Jupiter, it's about, like I said, it's about 10 hours. And then if you remember, I had that one slide that had like wind speeds that were several hundred miles per hour. So those wind speeds are all relative to that like 10-hour rotation, right? The same way on Earth, we talk about the wind is 10 miles an hour. Like in absolute terms, the Earth is rotating underneath us at like 1,000 miles per hour. So the actual wind speed would be like 1,010 miles per hour. But we say 10. The same thing on Jupiter, right? The whole thing is rotating once every 10 hours, but then on top of that, you have these couple 100-mile-per-hour winds, creating these bands back and forth as you move north to south on the planet.
Okay, speaking of the figures that you showed, one of them, like you always, whenever I see Jupiter, I always had the Great Red Spot on the bottom. The one that you're showing had it on the top, like in the northern, or I can't remember if it was labeled the northern or southern hemisphere. Is there like a special reason for that? Because that totally threw me off.
No, that was me not able to find a good diagram that didn't flip. I think what's happening there is that I think it's through well, Michael, you know this. It's through a telescope, so the telescope flips everything upside down. So
Okay.
That's what's happening, and they didn't bother to flip it back before they made this diagram.
Okay, and then last question. If we know the answer, why is the Great Red Spot red?
Why is the Great Red Spot red? That is known. I'm trying to remember. So it tells you what the Great Red Spot is made out of. So I'm trying to remember what the Great Red Spot is made out of, and it is completely like lost in my mind. But what that's telling you is that the Great Red Spot, like it's red because whatever is causing that red color, some chemical that I can't remember.
It's red because it's red. Come on.
Right. And well, it's actually fascinating, right? Because like whatever's also, this is part of the mystery of like what's going on there, is that it's concentrating all this stuff into this one spot and it's not letting it out. And like, why is that not happening elsewhere in the atmosphere? Nobody really knows. But right, it's red because it's made out of red stuff, and I can't remember the name of that.
Okay. Very cool. Thank you, Thomas. This is a super spooky and interesting talk. We really appreciate you coming out here. I think this is your third Astronomy on Top State College talk, isn't it?
I believe it is. At a certain point, do I like get a prize or something?
we can talk.
All right, we'll talk offline.
All right. Thank you again, Thomas. Thanks for stopping by. All right. So next up, we are going to do some trivia. And then I am being told that we do have a special guest who is going to deliver astronomy in the news. So be sure to stick around for that. I posted the link to trivia in the chat. I'll post it again in case you didn't see it. And so I'm going to hand this off to Arvind, who is going to take over for trivia. So go ahead, Arvind.
Well, all right. Thanks, Michael. I am sharing the slides right now. Can you see them?
Yes.
Awesome. Sounds good. Okay, yeah, this is not the answers that I'm sharing. That's important. So Jacob has asked me to remind all of you that this might be a good trivia round to have a pencil and paper ready for. You might need to write some things down or hash out some letters and words because it is Wheel of Fortune style. Yeah, before I get started, so here's the link to the trivia down at the bottom. And the way this works for those of you who have not been tuning in or who never went to our in-person events is that I'm going to ask you all a series of 15 questions. You'll submit your answers through this URL down here. It's a Google form. And then the team with the highest score at the end will be given some prizes, which I'll show on the next slide. In the event of a tiebreaker, since there are only 15 questions, I will choose the winner based on whichever teams have the highest score, based on the most creative team name, in my opinion. Sorry, the most creative astronomy themed team name. So try to think of something nice if you think you will end up with a high score. So yeah, the prizes that we have some Astro on Tap State College magnets, bottle openers courtesy of the Central Pennsylvania Observers. That's our amateur astronomy organization in the area. We also have some Astro on Tap beer koozies and some really nice astronomy themed masks from our friend Macy, who kindly sewed them for us. Yeah, so this week's trivia theme is Wheel of Fortune. What that means is that I will give you a word or phrase with a set of blank and filled in letters, and you have to figure out what the missing letters are to complete the word or phrase. In every case, this will be some astronomy themed term. A lot of these are, I tried to make them spooky. Not too many things in astronomy are that spooky though. So I've also taken some inspiration from terms that would have appeared in Thomas's talk or that will appear in the following talk. And also deviating from typical Wheel of Fortune norms, the letters that I am giving you off the bat come from the words spooky stars. So you'll have the letters S, P, O, K, Y, T, A, and R. So those will already be filled in. Those will not be any of the missing letters. The missing letters will come from the rest of the alphabet. So for this example here, with the letters that I've given you, hopefully many of you should be able to figure out that the correct term is exoplanet. Okay, so that was the example, and I will get started with number 1 right now. So this is number 1. Oh, sorry, let me go back. Yeah, so normally for these, I guess I would give you guys a few fun facts or some sort of hint about what the word is, but I think that would be pretty hard this week to do without giving away the answer. So this is number 1. Here's number 2. I'll also go back through all of these at the end. So once we get through all 15, I'll go back to the beginning, start over, and go through them again. Just because I know it might be a little difficult if you're not writing them down to remember what the letters were, what the blanks were, as you sort of figure this out. Number 3. Yeah, and also as a reminder, actually I didn't state this yet, but in keeping with past months of Astronomy on Tap, we ask that you do submit your answers prior to the end of Astronomy in the News. So directly following trivia, we'll be doing Astronomy in the News. And once that is over, I will start grading the answers and making sure that I know who the winner is. So here's number 4. And yeah, directly after this, we'll have a special guest for Astro in the News. I actually don't know yet who the guest is, but I'm told that it's going to be something exciting and also maybe spooky. Here is number 5. For number 5, we've also taken a page out of the Wheel of Fortune book and made this before and after themed. So for those of you who are unfamiliar with Wheel of Fortune, who never watched it at home, what this means is that the middle word here is both the first word of the second term and the second word of the first term. So the first word and second word here together make up a term, and then the second word and third word make up another term. Both of them are astronomy themed, but they are independent of each other. The only thing they have in common is that they share this middle word here. I hope that made sense to everybody. Here's number 6, a really fun one. Here is number 7 for this round. And I realized that many of these might be a lot easier than others. I tried to come up with words that were all sort of equivalently difficult given the letters that I gave you. But there are definitely going to be some cases where some jump right out and are obvious, and others where we'll be lucky if even one person gets it right. Here's number 8. I will also consider alternate answers that could be correct given all the rules. So if, for example, for this one, you provide an answer that isn't the correct answer, but is one that still fits in all of the themes of astronomy and spookiness and satisfies the letter requirements, I might still give your team credit for it and highlight those alternate answers when I share the trivia answers. Number 9, I apologize to those of you that are not astronomers. You probably won't get this one, but those astronomers in the audience may be happy or very sad to see this term coming up. Number 10. $11. And remember, there are a lot of the missing letters could come from some of the most common letters in the alphabet that would normally be given in a similar Wheel of Fortune clue, but which I'm not giving here because we're sticking to only these 8 letters at the top for the freebies. Number 12. $13. $14. This one might be the most difficult of the lot, but also one that astronomers consider very spooky. That could be a hint for some of you. Oh, actually, sorry, my mistake. This third letter here is an S. I don't know why I didn't fill that in. So this is an S. It's blank blank ST. That should have been given. So I'll state that again when I go back through all of these. Blank blank ST. And last but not least, our good friend, this guy. So I'm about to go through all of them again. I'll just put about 10 seconds per slide. So if you haven't written them down yet, that might be a good idea, just so you can make sure you're not blanking on things when you go back through the answer sheet. But after this, we will be moving on to astronomy in the news with our special guest. So here's number 1 all over again. Number 2. Three. 4. 5. 6, 7, sorry, 8, 9, a long one, I apologize. 10, 11, 12, 13, 14, and a reminder, this is the one where I messed up. It should be blank blank ST. This third letter is S. And 15, last one. So just remember to get all your answers in before the end of Astronomy in the News. And then we'll come back after the second talk to go through the answers and find out who the winner was. So thanks, everybody. I will now pass it back to Michael, I believe.
All right, so we are going to go ahead and do our Astronomy in the News with our special guest. So I'm going to go ahead and hand this over to our special guest, Chewbacca. Good to see you. Oh boy, that was pretty spectacular. Thank you, Chewbacca, for that very insightful reference. We're glad to have you out. Of course, it's Astronomy on Tap now. Not going just international, we are going intragalactic today to bring you Chewie. We did not know this was going to happen, but we very much appreciate it. All right, let's get on to our second talk. So we are going to have a. I'm sorry. We are going to have a group effort tonight. We have a wonderful group coming all the way from Northwestern University to tell us about spooky exploding stars headed by Dr. Raffaella Margutti here. So I'm going to pass this off to Raffaella here, who's going to introduce her team and tell us all about spooky supernovae. So go ahead.
Thank you, Michael, and thank you, everybody, to have us tonight here. So I'm Raffaella Margutti. I'm an associate professor at Northwestern University. And with my team at Northwestern, we study violent explosions that happen very far away in the universe. And tonight, I'm extremely excited to have the honor and privilege to introduce three of my collaborators. We're gonna hear from Lindsay DeMarchi, Wynne Jacobs-Angelan, and Candice Stauffer. And I believe that prepares something very special for you all and definitely very spooky. Take it away. Thank you.
Thanks, Ralph. Awesome. So, like Ralph said, my name is Wynne, joined by Lindsay and Candice, and today we're going to talk to you about the spookiest astronomical occurrence of them all, the death of a massive star, or just any type of star. So we're going to be talking about stellar autopsies and supernova explosions. That's the title of the talk. And today we're going to be looking at this thin shroud between life and death. So when a star is living and when it dies, we want to think about what does a star do right before it dies, and then going on into what do we see in terms of this violent stellar eruption or stellar explosion that is a supernova on the right. So this is a brilliant supernova 2011 FE in its spiral host galaxy. And when a supernova explodes, it can violently and luminously produce more light than it can rival the luminosity of the host galaxy it's in. So we want to understand how that star was living right before it died. And the answer is really at the beginning. So if we look back and we see how this star is exploding, we can then understand how it lived prior to death. And as a moral technique said, death is just another part of life. So I'll let Candice take it from here.
Yeah, thanks, Wynne. So on theme with our spooky topic tonight, I want you to imagine that a supernova has gone off and we're left with a dead body or the corpse of a supernova. And so we want to recreate its final moments of life. And so we, as stellar morticians, are going to are performing autopsies on these supernovae. But instead of scalpels and embalming machines, we're going to use, the tools we're going to use are those of the electromagnetic spectrum, but spread across different wavelengths. And so each of us will specialize in a dissection at these different wavelengths or energy ranges. And then go to the next slide. Thank you. Okay, so the ranges we're going to be talking about in the electromagnetic spectrum are the X-ray and optical and radio. And so you can imagine it as if we're wearing different glasses to see different organs of this supernova corpse. And many of the images you see, like when you Google nebula or different images of space, give us a combination of all of these different wavelengths of light, like the one you're looking at right now. But the first wavelength we'll talk about is in radio. So the radio waves operate in frequencies from around 300 gigahertz to as low as 3 kilohertz. And they're not actually sound waves, but like the rest, a form of electromagnetic radiation. So these are the same forms of electromagnetic radiation that transmit music and the talk shows you hear on AM/FM radio, Wi-Fi, cell phone signals, and TV. And in those machines, they work by receiving the radio waves and converting them in a radio circuit and turning them into an electrical signal, which is pushed through an amplifier, and that's how we hear noise. But supernovae radiate the same kind of electromagnetic signal. And this is what we will use to dissect, or one way we will dissect our supernova and look at some of its organs. So when we're trying to tell the story of a supernova explosion in radio, we're looking at the largest scale. So this part of our autopsy sends us radio waves. And so this is another image of a corpse from a supernova, and it's left behind stellar remnants. And we call this one Cassiopeia A. It's about 10 light years in diameter, and it exploded over 300 years ago. So it really makes Cassiopeia A truly like the ghost of a supernova that once occurred here. And this image you're looking at is actually composed of optical wavelengths from Hubble, infrared, and Chandra X-ray images all overlapped together to help you see the colors you're looking at here. And the shock of this supernova is expanding into the interstellar medium. And as it does so, radio emission from this supernova comes from a shock wave produced by this explosion slamming into the material around it at 10,000 kilometers per second. And this likely comes from the star that produced the supernova just before the star died. So this interaction between the shock wave of the supernova blasting into the surrounding material produces something called synchrotron radiation. And that's the illustration you see in the top right corner, drawn by yours truly. And this is produced when a particle, so either a proton or an electron, is accelerated through a magnetic field in that kind of spirally pattern that you're looking at. And the longer the electron travels around that magnetic field, the narrower the spiral it makes, the longer the wavelength of the critical frequency is, and the more it kind of decays. And the synchrotron emission doesn't depend at all on the temperature of the supernova, but just on the strength of that magnetic field. So the larger the magnetic field is, the greater the intensity and frequency of the emitted radiation, the cry of help the supernova gives out as it's dying. So if there's a very strong magnetic field, the energy of the particles will be even greater. And the image on the right that just popped up is the very same corpse of Cassiopeia A, but it's just specifically in radio. So that's looking at Cassiopeia A with your radio glasses on. And so with that, I will take my radio glasses off and we'll pass it over to some optical lenses, which Wynn is going to tell us more about.
Yeah, so I'm going to put on my optical glasses, which are just regular glasses, because that's how we can observe supernovae too. We can take, just like we take images of ourselves with our phones and take images out in the real world, we can do the same thing with supernova explosions. And this is when a supernova is freshly initiated. This is when the star is freshly dead. And so what we can see here is a newborn stellar death superimposed on its host galaxy right there. So that bright, shiny burst of light is actually the death of a star. And as the astrophysics CSI team arrives on the source, what we can do is we can take a lot of images in the optical bands, and we can split those up into a prism essentially, and produce blue wavelengths of light, red wavelengths of light, and make this composite image, which is just a spectrum, a supernova spectrum. So it's just a wiggly signature from the supernova, from the star that has died. And all those wiggly lines correspond to different elements that the star has produced when it has violently erupted and died in this supernova explosion. So we get a little calcium, we get a little iron. All of these are in our bones. The stellar death, the deaths of stars, give us our bones, give us our spooky life we have here on Earth. And I can look at this spectral signature from just looking in the optical, and I can say this star was likely a compact white dwarf, so what our sun will turn into when it dies. And that compact star has violently exploded and produced all these fun elements and bright light that we saw by just splitting it up with a simple prism. But the freshly dead star is not the only thing that we can study. We can look at this star for longer periods of time, like Candace showed with the radio, but we can still do it with our optical glasses on. And we can study a star throughout its history in optical bands. So what I'm showing here is a time lapse of a supernova explosion rising and fading in brightness. So what it's doing is it's cooling down as it's expanding into its interstellar medium. and it itself is actually dying. So it is cooling off, it's producing less light, it's rising to its peak and it's fading away. And this so-called light curve of a supernova also tells us what type of star produced a given supernova, because different supernovae will have different light curve signatures and will evolve differently in time. So we can use that in our stellar autopsy to kind of turn back the clock and look at and try kind of put our finger on what type of star was living prior to its explosive death. And I'll turn it over to Lindsay.
Okay. So if we look at this moment again with our X-ray glasses, the moment a star erupts and a shock surges across the surrounding space like a harbinger of death, X-rays allow us to look at the most energetic moments of stellar demise. So very much the same way that we're familiar with X-rays on Earth, whispers from the recesses of space permeate our skin and our planet all the time. Invisible to our eyes, X-rays are the very same that we would use in the dentist's office, in the doctor's office. It's the same process, but we receive them one photon at a time, illuminating dark secrets surrounding stellar death. If we were to take an X-ray of a long dead star, it would appear as the ghostly image in the time lapse on the left. If you look very closely, you can see some small changes taking place over the course of a few months. That dot at the very center there is the corpse of a once boiling, thriving star much larger than our sun, now compacted to the size of a city. This Jane Doe is called a neutron star, an incredibly strong cousin to the black hole, but slightly larger. And I literally mean larger, even though black holes will compact thousands of suns into its size. It comes out to be about smaller than the size of this period here. To the right, this haunting crime scene image is zoomed in on the edge of a galaxy before and after a supernova explosion. As a star ages during its life, it coughs violently. These frenzied outbursts leave stars to lose some of its mass, and it pollutes its surroundings, only to be remembered when the dead star's shockwave travels through it again posthumously. As the shockwave eventually encounters the residue of lost ages, it immediately ionizes the ancient elements and sends individual photons in all directions, some reaching us. As a mortician, I think of capitalizing on this 2-for-1 moment, like on the right. We learn about the shockwave of the fatal explosion, but at the same time monitor its death rattle years before it died. And so we receive X-rays from all moments of this dying process. We use data like this to tell us the exact moments the innards have erupted from the surface of a dying star in one final heave. This is called the shock breakout, and it explodes in a burst of X-ray light, just like in the video we showed, when your screen flooded with white and blinded you momentarily. This is the shock breakout in the X-rays, as well as the strength of the shock wave as it travels from the star, immolating and ionizing its surroundings farther and farther into the vacuum of space. The same charged particles that created synchrotron emission when you were wearing your radio glasses can be slowed down and interrupted. This is called Bremsstrahlung radiation, and it emits in the X-ray. That is one of the clearest places to see it, even though you can also see it in the radio. And so as stellar morticians, we use all wavelengths as members of Raffaella Margutti's team to combine and reveal the before, during, and after a stellar demise. This is how we put together a composite image and a cohesive narrative, like you see here in the result. Just like Wynn said, the end is the beginning and the beginning is at the end, what you're looking at here. When a star dies, it doesn't just explode. It heaves itself inside out in a fiery death that ignites and its insides spewed outward and destroys everything in its vicinity. In our autopsy, we use the optical portion of the spectrum to tabulate exactly what elements were present or formed in the heat of this moment of initial explosion. From there, we use radio and X-ray photons to track how quickly the shock crawls through space over remnants of its own corpse in order to reconstruct how it once lived in the very moments before it died. Once the dust of the explosion has settled decades to centuries later, we can return to the scene of the crime and behold the blazing glory of a neutron star or stare into the gaping maw of a black hole. Thank you.
All right, that was sufficiently spooky. I am very spooked. Thank you very much for that talk. That was amazing. Again, if people watching on YouTube, if you have questions, please go ahead and type them into the chat here so we can go ahead and ask our speakers. So I guess one question that I have is you're talking about these light curves. You have a star that explodes and you get this peak in brightness and then it starts to come down, it fades away. And you mentioned that different supernovae can have different light curves. So what might those different light curves look like? And do they look different in optical versus radio versus X-ray? Or do they all have the same kind of properties?
So maybe I can take the first part of that question, which is just about the optical light curve. And yes, exactly. Different supernova explosions, so different stars exploding will produce different light curves. So that little animation that I showed you was probably most similar to a white dwarf, like a compact, very compact star that explodes. Its temperature, radius, and luminosity will change as a function of something parabolic. It'll go up, it'll go down. And how fast it goes up and how bright it is will tell us that probably came from some sort of white dwarf. However, like a more massive star, like a big puffed up red supergiant, will rise pretty bright and then it'll kind of plateau because its outer envelope is really hot and the hydrogen there is trying to recombine. It's trying to get back to a state of equilibrium and it'll kind of hang there for a little bit and then fall off. And then there's some that will rise for years or months, and that will have to do with interaction with some sort of gas that the star has shedded prior to living, and that's generating some energetic processes that are keeping the light curve alive for a long time. So yeah, definitely different, but all very revealing.
Okay, and I guess the second half of that question is kind of what does the curve look like in, I guess even do you see a curve in radio, or do you see a curve in X-ray where this thing will start to peak in brightness and then decay?
Yeah.
Go ahead, Kate.
No, after you.
I was going to say, at least, so part of what makes it so difficult, but also so fun, is that you don't get all the pieces of the puzzle at the same time. So when a star dies, it is so dense and so hot that different wavelengths escape the environment at different times. So I mentioned in my talk, the shock breakout is X-ray. So X-ray is one of the most energetic photons, and that's what'll reach you first. And then you'll have to wait sometimes hours, sometimes days, sometimes even longer than that to get the other pieces of information, even if they all originate from the same process at the death site. To escape the surroundings takes a long time. So sometimes you're piecing together parts of a story that are all talking about the same moment, but coming to you months and months apart. So in X-rays, at least, we kind of have this like unofficial saying, like no photon left behind, because sometimes you can count the individual photons that come to you, like on the order of like 8. So a light curve coming from X-ray definitely is not as, I guess, illustrative as it would be in the optical, at least. And Candace, I'm sure you wanted to talk about radio light curves also.
Yeah, I mean, I think you guys said it pretty well, just that the different light curves are coming to us at different times and tell us different things about the supernova. So back to that analogy, they kind of let us dissect it in certain, in different ways, I think, yeah.
Okay. And then there was a plot you showed where you have this slight curve, and you have different absorption bands in there, where you have things like calcium, or spooky star stuff in our bones that came from these exploding stars. So we know that the sun and maybe some other stars as well, they're not just hydrogen and helium. We do see other elements in there like iron and calcium and a whole bunch of stuff. So is there a way to know like how much of that material that we see in the slight curve formed during the supernova, or was it kind of there originally in the star that blew up and then maybe more was created?
Yeah, definitely. So like the scenario that supernova spectrum that I showed was from a white dwarf that exploded. And we're pretty confident that white dwarfs are pretty much just carbon and oxygen, like what our sun will be. And like you said, there will be like trace amounts of tiny little elements, like iron and maybe a little calcium, but realistically, those are almost non-existent until the supernova goes off. So we really need explosive processes in the universe, like supernova explosions, to make the the heavy elements in our blood, the heavy elements that we use for nuclear processes on Earth. So to quantify that amount of stuff, we need to look at a supernova spectrum like that, and we need to model it and try to understand how much light is emitted from a given, I guess, element or ion at a certain time. And that can help us quantify the amount of different stuff that is made in the supernova. But almost exclusively, those elements are made in the explosions of stars. And it takes a very, very long time to make them otherwise.
Okay. And so let's say then that we're living around a star that does blow up. What happens to us on Earth? Let's say, you're living on the surface, or maybe you're even on the other side of the planet, the star goes off and you're on the other side. Would people survive? Would the planet itself survive?
I don't have much
No.
faith for the human race being there when the sun even explodes it off. So, but the sun won't explode. But no, we're toast.
If the sun explodes, was that the question?
Like if the sun itself blew up, what happens to the Earth? What happens to the planets? What happens to the people on those planets?
So I think the Earth is totally engulfed, but Mars, I think, or if the sun explodes, I mean everything is over. But I think once the sun, gets to its like its giant fate, because it'll expand very large before it goes out. But I know that once the sun does reach that point before it's about to explode, when it gets very large, up till Mars is still like in the safe zone. So I don't know, maybe that's more of a reason that we need to go to Mars. So when the sun's about to explode, we can.
In a few million years, I'm sure the human race will at some point get proactive and figure this stuff out. All right, so if you're a mortician, you've got your patient on the slab, you cut open your white dwarf, your neutron star. What do you find inside? What kind of entrails are there?
Can I take this one? Okay. This, you have struck on, Halloween or not, one of the spookiest questions in astrophysics. I don't know if you did that on purpose. So, okay, the coolest way to frame this answer is to think about water, okay? So water, we understand pretty well that when it gets to a certain level of too hot, it turns to steam. Too cold, it turns to ice, right? So we can track its motion through solid, liquid, gas pretty easily. This is unnecessarily given many syllables, called the equation of state. So we understand from materials, different materials, the conditions under which it'll go through these different phases of matter, solid, liquid, gas. So, oh man, I just want to like dive headlong into like what these stars are like on the inside. But for a white dwarf, you have gravity that is so strong that the way I like to phrase it is it's pure math holding it up at that point. It's something called electron degeneracy pressure, which just means that if you look at an atom and you think of an electron cloud around it, you are smushing all of the material in a white dwarf so close that the electrons complain that they are too close to each other. And they say, no more, We're not letting you crush me down any further. Okay, so that kind of material is a little strange when you get to that level of compactness, but we understand it okay. We understand it relatively well. What makes up a neutron star, the reason it's called a neutron star, is that gravity is so powerful that it says to those electrons, I don't care that you don't want to be close to each other, too bad. And it pushes them past that threshold. And now it's the neutrons saying, oh my God, too close. I can't be any closer than this. And it is the neutrons that are pushing back against gravity and saying, no, I don't want to do anything past this. The material that behaves that way, we do not understand at all. The neutron star equation of state is a completely open question. And it's what I find so enticing, because normally gravity, even though we experience it every day, it's a very weak force. And a neutron star's gravity is so powerful that if you put Mount Everest on the surface, it would fit in a teaspoon. That's what it means to overcome electron degeneracy pressure. So long answer short, I don't know.
We don't. So kind of branching off on that real quick, there's, you got these exotic states of matter, you got neutrons. Quark stars are something that's kind of been thrown out there. Do we know what a quark star, like a supernova that would produce a quark star, what that might look like in X-ray and radio or in optical?
To take a stab, only because I see Candace and Wynn shaking their head and because I love talking. To take a stab, this answer is another question, which is, would a quark star be stable? So the issue is, for anybody who doesn't know what a quark star is, I'm animating these electrons, animating these neutrons. And so what if we got to the point where we said, okay, I don't really care, neutrons, about your personal preferences. Neutrons and protons are made up of even smaller pieces called quarks. So what if we got to the point where it was just a quark soup, like at the very beginning of the universe? That's a quark star. So the question is, and it's a very viable question, if there was a quark star, what would that look like? And like I said, kind of a while ago, when a star dies, the surroundings are so dense and so hot that information and electromagnetic signals can't get out. So if there was a quark star, it might not live long enough to tell us that it exists. So if you wanted to learn anything about a quark star, you would have to magically see in through those true moments, like seconds, that's invisible. And this is actually where gravitational waves become so important, because gravitational waves don't care about the electromagnetic spectrum, they care about space-time. So this is like a whole other branch, but I promise people think about it.
All right, this has been very informative, very spooky. Thank you so much for coming out here, Lindsay, Wynn, Candace, and Raffaella, for introducing everybody here and getting her group to come out. Thank you all very much for giving us this wonderful talk tonight.
Thank you, guys.
Thank you.
All right, so we are going to get our trivia answers. So I'm going to pass it off to Arvin real quick. You're going to tell us the answers and tell us who won tonight's fabulous prizes.
Thanks, Michael. Yeah, and thank you, Northwestern folks, for giving us a great talk and really running with that spooky theme, even if it did make me a little bit more pessimistic about the future of our planet. So here are the answers for trivia. I'm going to assume you guys can see these unless Michael comes back out and tells me that you can't. So, and as a reminder, these are the prizes that are at stake. So good luck to all of you. Number one, here was the clue, and the answer for this was black hole. So kind of spooky objects, right? They suck things in and destroy them. Really strong gravitational fields. Number two, here's the clue. The answer was a fast radio burst. These guys, I think a little bit, as of a few years ago, when I was paying attention to the research on these, we had no idea what they were, which makes them kind of spooky, although I think there may have been a little bit more recent research that gave us a bit more insight. I'd probably have to check with my radio astronomer friends because I don't really study these. Number 3, nobody got this one correct, which is kind of in keeping with how spooky they are. These were magnetic fields. There's a common joke in astronomy where if you don't understand why something is the way that it is, you say, oh, it's probably magnetic fields because we don't understand them, and they're a good way to explain things we don't know how to explain. Number 4, this was, you'll hopefully recognize it from that second talk there, supernova remnant. This is kind of what remains after a star dies and after a supernova happens. Number 5, this was the fun before and after question. This was the Tunguska event and the event horizon, which together makes the Tunguska event horizon. The event horizon is the edge of a black hole beyond which no light escapes. The Tunguska event was a meteor that entered the Earth's atmosphere and exploded, and I think it flattened trees for, I don't know what radius, but it was a huge radius around. And the only reason it didn't end up killing a lot of people is because it was in the middle of nowhere in Siberia where nobody lives. But this was a meteor that entered our atmosphere and could have caused a lot more damage if it had been in a more populated area. Number 6, a really fun one. This is syzygy. You're only missing 2 letters, but if you didn't really know what the answer was already, it would be hard to figure what they are. A syzygy is when all of the planets or all the bodies in a system align in a straight line. So if you imagine that from the sun, then Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto were all in a straight line down from the sun and not being in different angular orbital positions, you would call that phenomena a syzygy. Number 7, the clue and the answers here are a Trojan asteroid. So these are asteroids that are in the same orbit as the Earth, so the same distance from the sun, but they are in a stable orbital plane or a stable position such that they continue going around the sun while staying in equilibrium with Earth, so they'll never collide with us or anything because they are they're gravitationally stable. Number 8, answer was solar flare. So you haven't heard of solar flare. It's a really energetic event on the sun when magnetic fields, as we talked about before, do fun things and release a lot of energy that can actually cause things to happen on Earth, maybe interfere with electrical or magnetic things here on the surface. Number 9, if you weren't an astronomer, you probably didn't have much luck with this one. The answer here was Bremsstrahlung radiation. That first word here is German. It means breaking radiation because it's radiation that is emitted when charged particles in outer space interact with each other. Charged particles that are moving at relativistic speeds interact with each other, and the energy that's released during that interaction is radiation that we observe. Number 10, I'm sorry that there were no letters given to you in the first word here, but the answer was Hubble constant. A lot of people got this one correct, so congratulations. There probably were a few other possible answers that I didn't think of and that nobody else thought of, so I'm glad people figured it out. Number 11, this one was lunar eclipse. Somebody put solar eclipse here, but that would not be correct because the S and the O would already have been filled in if that were the answer. So 11, lunar eclipse. This is when the Earth passes between the sun and the full moon at night, and we observe the Earth's shadow crossing over the moon, and the moon takes on a reddish hue as we see sunlight passing through our atmosphere en route to the moon. Number 12, I already showed this, so I'll just go through it again. This is dark energy. I think most people got this one correct. Number 13, this one you probably should have recognized from Thomas's talk if you were paying attention. The answer here is hot Jupiter. So these are Jupiter-sized exoplanets that are very close to their host star, which makes them have very high equilibrium temperatures, something like high hundreds to thousands of Kelvin, and which makes them, of course, very hot. And they're often in orbits that are much shorter than the orbit of Mercury around our sun. Number 14, I messed up the clue for this one, but the correct clue is given here. It's just blank, blank, ST. This one is also considered very spooky by many astronomers. The answer is dust. Dust can obscure things and make them difficult to observe and difficult to understand. It can cause us to misinterpret our results if we don't properly account for it. And one of the best ways to get around dust is by doing multi-wavelength observations or observing in the infrared, where the impact of dust on light is a lot weaker. Number 15, the last one, and in my opinion, the spookiest. This was the James Webb Space Telescope, which I think was supposed to launch in 2012, and then was delayed many, many times. It is now expected to launch about a year from now, early October 2021. And if all goes well, it will. But based on its track record, we don't really know that that is going to be the case. So without further ado, the winner was Team Dark Energy. They had 14 points. The only one they got wrong was magnetic fields, which everybody got wrong, and adds to the fact that magnetic fields are incredibly spooky and difficult for astronomers to deal with. A fun fact about dark energy is that the Department of Energy in the United States actually funds dark energy research, even though dark energy probably doesn't have anything to do with energy that can be utilized for practical purposes here on Earth. But it's a nice way for astronomers to get extra funding, and hopefully nobody in that Department of Energy wises up to the truth of this. So if you were Team Dark Energy, look out for an email from us in the next few days. I'll let you know what the details are about how you can get your prize, and congratulations on winning. So with that, I will hand it back to Michael to wrap up.
All right, thank you, Arvin. Thank you, everyone, for coming out tonight. I think I can say this has been one of my more favorite events that we have done, either in person or virtually. So thank you to Arvin for trivia. Thank you to Chewbacca for coming out all the way from a galaxy far, far away to give us astronomy news. I hope you kept that on the entire time, since astronomy and news too. All right, we will be back in November. And of course, I do have to say that the U.S. election is coming up pretty quickly, and I think the spookiest thing of all is a nation that does not vote. So if you haven't already, please do take the time to vote. If you have your ballot sitting around at home, go mail that out tonight or tomorrow. Thank you again, everyone. Thank you, Thomas. Thank you, crew from Northwestern University.